So the question becomes, how do we actually figure out these orders? How do we figure out what impact each of our different reactants have at a given time? And based on that, what our kind of rate constant, or K, would be as we were looking at a reaction. So here we've got some sample data. We've got nitrogen monoxide reacting with oxygen to form two nitrogen dioxide molecules. And we know that the rate is going to have these two reactants in it. We don't know with what respect our different reactants have, what effect they have on the rate of the reaction. We don't know what the constant is. We're gonna have to figure all of that out. Well, the good news is we got data. We can go back in the lab and we can start to change things. We can say, okay, how long did it take my reaction to change? How long did it take for my rate to go, for my reaction to go? And so that's what we did. We've got 5 different trials here. We might not need all of them. We've got 5 different trials here. And if you look, we've actually changed the amount of starting materials. And then we measured how quickly did the concentration change over time. We actually measured the rate of the reaction in the lab, the change in concentration over time. And so in trial 1, we had some amount of oxygen, some amount of nitrogen monoxide, and we had a rate. Oh, so I guess we could kind of plug those numbers in then, right? I'm going to disappear for just a second. So that means we can actually plug these numbers in. We don't know all the parts, but we do know that for trial 1, for trial 1, nope, I need to back that up. Back it up. Discard that. For trial 1, we know that the rate is going to equal, so that 3, let me discard up. Maybe, oh my goodness, the tech is real today. Okay, there's that. All right. All right. So we actually know some numbers. We know that the initial or the rate for our first trial here, 3.21 times 10 to the negative third, is going to equal some constant K times the concentration of our oxygen, which we knew, right? We measured that. We knew how much we put in at the beginning. It was 1.10 times 10 to the negative third raised to some power. We're going to just call it M. We don't know what it is. And then we had our concentration of our nitrogen monoxide. It was times our 1.30 times 10 to the negative second. Oh, they're both negative second. Sorry, guys. Negative second and negative second raised to some nth. Oh my goodness, I need to start over. I ran out of space. But we can plug in what we know. We know for the first one, sorry, let me get it a little cleaner here. It was 3.21 times 10 to the negative third equal to some constant, which we don't know, times our oxygen concentration, 1.10, 10 to the negative second, raised to some nth power, times our 1.30 times 10 to the negative second, raised to the nth, right? We don't know what the M and the N are or what the K is, but this is what we know. We have some numbers for a lot of this piece. And now we can look at trial 2. Well, what do we know in trial 2? If we look, it looks like we have doubled the amount of oxygen. We doubled the amount of oxygen that we used, but we kept the nitrogen monoxide the same. Ooh, that's going to be important. So we know in trial 2, and the rate did in fact change. That must mean 6.4 times 10 to the negative third is going to equal some constant K. We've got a change in our oxygen, which is 2.20. We doubled it, 2.20 times 10 to the negative second, raised to some power N, times, it's the same, times 10 to the negative second, raised to some power N. Sorry, that's an N. Good news though, because we're gonna be able to get rid of some stuff here. If we actually take the top one and divide by the bottom, some fun math happens here. So we're gonna divide. Well, if we're thinking just about kind of our second term here, we got the same exponent on top and on bottom. We got the same mathematical values. Those actually are going to cancel out, which is super handy. And K is a constant at the same temp. The K's cancel out as well. And so mathematically speaking, a fun little thing happens here. We now have 6.40, times 10 to the negative third over 3.21. times 10 to the negative third is now equal to our 2.20 times 10 to the negative second over, and that's raised to the nth, but we're going to do a little math manipulation here, 1.10 times 10 to the negative second. And if both of these are raised to the nth, we can actually say that this whole fraction is raised to the nth, which is really nice because we're trying to find out one of those exponents. And so if we pick two that are the same for one of our concentrations, they drop out. In this case, the nitrogen monoxide is dropping out. And now we can actually solve. I think if we take the left-hand side and we solve, we get, I think, 2. We're going to have on the right-hand side 2 to the nth. Well, 2 raised to what power gives us an 2? Well, I think it's going to be n equals 1. And I think if we're going to try to pull it out in front, we're going to have to do some logarithm works, right? If we try to bring the exponent out to solve for the exponent, hopefully we'll see some examples of that here in just a second. Cool. So now we know n. N is 1. So that means there's a direct relationship between changing the oxygen concentration and the rate of the reaction. Cool. Let's look at the other piece then, because we also need to get our nitrogen monoxide, right? So let's look for two reactions where the nitrogen monoxide changed, but the oxygen didn't. I think if we're looking here, I think we've got reaction 1 and reaction 3, right? Your oxygen stayed the same, but your nitrogen monoxide didn't. So we would use our new rates. We're going to set up just like we did the last one. We've got 12.8 times 10 to the negative third over our original, which was 3.21 times 10 to the negative third. Sorry. That's going to equal, we got K. We had our 1.30. Sorry, we're doing our trial 3 on top, I think. We got our 2.6 times 10 to the negative second raised to the nth. M we just found to be 1, right? Sorry, I think I flip-flopped it in the video. I started saying N. Should have been M, right? And the N's canceled out. We found M to be 1, first order with respect to oxygen. Now we're trying to find our N. Well, it's going to be K times our original was our 1.3 times 10 to the negative second, also raised to the nth. I think our K's get to cancel here. We'll combine our N's. 12 divided by 3, I think is going to be a 4 on the left-hand side. 2.6 divided by 1.3 times 10's parts cancel out. I think that's going to be a 2 raised to the nth. Well, 2 raised to what power equals 4? I think N has to equal a 2. Oh, so now we know N. Cool. Oh, I keep grabbing the top. So now we know N. N's a 2. It's second order with respect to our nitrogen monoxide. Well, now, if we know those values, we can pick any of the trials to solve for K. We now have all the exponents except for K. We can pick any trial. I'm going to do trial 1 just for the sake of simplicity. We know that our rate, 3.21 times 10 to the negative third, is going to equal some constant K times our 1.10 times 10 to the negative second. Oh my goodness, my pen is struggling. Negative second raised to the first power. Ooh, I'm out of space. I apologize. That's also going to be times, in this instant, our 1.3 times 10 to the negative second, quantity squared. We should be able to multiply and then divide over and solve directly for our constant K. So good example for us to be working through these calculations. We'll be looking at some more of these when you come back in class, but I wanted you to preview one prior to coming back and working together.